Hey everyone, I want to show you how to solve something I call the overlap problem in integration. The overlap problem is a problem where you have a bunch of statements about the value of an integral, a definite integral, from different endpoints. So this question, we're asked for the antiderivative or the definite integral of f of x from 5 to 10, and we're given information about the antiderivative from 0 to 10, 0 to 100, and 5 to 100. And there's several different ways that we can approach this problem. I'll show you a few of them. They all rely on the following property. So I'll jump back to the question, but I want to go over this property and explain why this property is true. The property is that the integral from a to b of f of x dx can be rewritten as an integral from a to c of f of x dx plus the integral from c to b of f of x dx for any c. You can split your integral at any point and treat it as two separate integrals. Do each one, add the results together. Here's two reasons why this is true. Reason one. So the first reason is I'm going to let capital F of x equal the antiderivative of little f of x. Okay, I'm just going to give it a name. That's the general antiderivative with the plus constant of integration with the arbitrary constant. That's not going to be important here. So with that, we can say that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. The integral from a to c of f of x dx is capital F of c minus capital F of a. And the integral from c to b of f of x dx is equal to f of b minus f of c. So we can put these results together. That integral from a to b of f of x dx, well, that's f of b minus f of a is equal to, now the second, so I'm going up to the yellow, so I replaced the first yellow term with what it's equal to from the below, and then the second term in yellow, integral from a to c, well, that's equivalent to f of capital F of c minus capital F of a. I want to make my brackets look different than c. And then plus integral from c to b, so capital F of b minus capital F of c. And look what happens, we have a capital F of c subtracted and added, so they're going to destroy each other. So that's the proof. I can just change the order of summation, f of b minus f of a. So on the left-hand side, I have the same thing as on the right-hand side. Here's your second reasoning. It was stated that the antiderivative of f of x evaluated from a to b tells you how much area is under the curve. So I'm just going to draw a quick sketch of some function, and the details don't matter. So here's my function f of x. I'll sketch in an x is equal to a coordinate and a b value. And what we're doing when we calculate this integral is we're looking at this area here. That's what is extracted from that integral, that result. And this is equal to, we'll draw two more graphs. I'm going to draw that function twice more. I'll do my best to make it the same. Okay, I'm also going to put in C in here. So I'll choose C as a pit stop in between. And then I'm going to shade in those areas. So if we're going from A to C, then that's this region. And if we're going from C to B, that's this region. So the statement that the integral from A to B is equal to the integral from A to C plus the integral from C to B is just a statement that if we add those two partial areas together, we get the entire area. So that's the algebraic reason why that property is true and the geometric reason why that property is true. And like every concept in mathematics, you could justify it algebraically, and you must also be able to justify it geometrically. I make that as a very bold claim that won't be explored further. So let's use that property here for this problem. We're going to have to be very creative how we, well, not that creative, we have to be a little bit creative how we do that. I'm going to pick the largest range of integration, so that from what covers the most x values, what covers the largest part of the number line. So that's the integral from 0 to 100. And I'm going to split that up. Looking at what I have here, I have an integral that goes from 0 to 10. And I have an integral that goes from 5 to 100. So that's a bit of a problem. I want to go from 10 to 100. So how can I go about doing that? Well, I'm going to take this integral, this integral from 5 to 100, I'm going to rewrite it. Integral from 5 to 100 is equal to the integral from 5 to 10 plus the integral from 10 to 100. So I'm going to use that here. So the integral from 0 to 100 is equal to integral from 0 to 10 plus the integral from, let's see if we can rearrange this. I'm going to get the integral from 5 to 10 on its own, or wait, I'm going to get the integral from 10 to 100 on its own. So integral from 10 to 100 is equal to the integral from 5 to 100 minus the integral from 5 to 10. So plus, so I'm replacing this with integral from 5 to 100 minus the integral from 5 to 10. And now we can plug in the information that we have. Integral from 0 to 100, we're told that that's 50. Integral from 0 to 10, we're told that that's 30. Integral from 5 to 100, we're told that that's 40. And then the last thing is unknown. Integral from 5 to 10. Okay, and then we can simplify. 50 is equal to 70 minus the unknown. Subtract 70 from both sides, so negative 20 is equal to the negative integral from 5 to 10. And that means, thus, the integral from 5 to 10 of f of x dx is equal to 20. So that's one reasoning that we can use. Here's a second approach. We can use a type of graphical approach. I'm going to draw just a picture. I don't even know what the function looks like. It doesn't matter. I'm going to draw a picture of it anyway. So here's my f of x. Here's 0. Here's 100. And I got special values at 5 and 10. I'm not going to draw them perfectly. Obviously, that's not an accurate representation of the number line. It doesn't matter. I just don't want to scrunch everything in. then we can do the following. We can trace this up, and trace this one up, and we have one of these shaded in areas. We have 0 to 10 is this one. So that's integral from 0 to 10 is equal to 30. So that much is 30. And we also have an integral from 5 to 100. Careful with my colors. I guess I'll use, let's see, blue, purples. I got color, too many, I need more colors. I guess I got some yellow. Okay, so that's this one. I'll hatch it the other way. So that's integral from 5 to 100 is equal to 40. So the region between 5 and 10 is what we're double counting. So I can say that the whole thing is equal to 50. So 50 is equal to 30 plus 40 minus the double counted. I have to subtract the double counted because it's being counted twice. So I'll explain that a little bit more. If something is counted twice, and you subtract it once, then it is only counted once. Kind of a very clean logic. So 50 is equal to 70 minus the area that represents what's double counted, integral from 5 to 10 of f of x dx. Thus, integral from 5 to 10 of f of x dx is equal to 20. So there you have it. There's your geometric reasoning for solving the problem, and you can compare it to the algebraic reason for solving the problem, and they're connected to each other. Those reasons are connected to each other because this property that we're using to split up the integrals, this property is equivalently stated algebraically and geometrically.